All right, welcome. Today we're diving into a story about a single drop of blood, a drop that has been quietly saving millions of babies for decades. Now, a huge technological revolution is about to unlock all the secrets hidden inside that drop, but as you'll see, it's not quite as simple as it sounds.
You know, for decades, this tiny drop of blood from a newborn's heel has been a quiet miracle worker. But what if, and this is the big question, what if we could read it not just for a few dozen conditions, but for hundreds? Well, that's the future we're stepping into right now.
Okay, so before we jump into what's coming next, we've got to understand the present. This entire system is built on a really simple but incredibly powerful idea. Detecting problems early saves lives.
Yeah, all the way back to the 1960s, the heel prick test has been a total cornerstone of pediatric health. It's this beautifully simple procedure that screens for rare but really serious conditions, letting doctors step in before a child even shows any symptoms. It's truly amazing. So the official term for this is newborn screening, or NBS. And the whole principle is to catch treatable diseases right at the beginning, when we can actually do the most good. It's a proactive approach that has completely changed the game for diseases like phenylketonuria, PKU, which, if you don't catch it and treat it with a special diet right away, can cause severe intellectual disability. It's a true public health success story.
Okay, so how does this whole screening thing actually work under the hood? Well, traditionally, it's all been about chemistry, but the revolution, that's about reading the source code itself. Let's break down these two different approaches.
All right, this is the really crucial part. The classic method, metabolic screening, it looks for chemical imbalances. Think of it like checking a factory's output, sniffing the smoke coming out of the chimney to see if the engine is running properly. The new method, genomic screening, well, it goes straight to the factory's original blueprints, the DNA, to look for typos that could cause problems down the line. It's incredibly powerful, but as we're about to see, just reading the blueprints isn't always so clear-cut.
Now, this new genomic power, it's incredible. But, and this is a huge but, it comes with this massive kind of unexpected challenge. It turns out that sometimes having more information can actually create more confusion, not less.
You see, the promise of reading our entire genetic code is amazing, right? We can spot disease risks super early. The reality, though, is that our DNA is just filled with tiny, unique variations. Most of them are totally harmless, but some of them can cause disease. The problem is, for thousands and thousands of them, we don't know which is which.
And that right there brings us to the central villain of our story, really, the variant of uncertain significance, or VUS. Imagine you find a typo in that factory blueprint. Is it a harmless spelling mistake, or does it change a critical measurement that's going to cause the whole building to collapse? That's the challenge of a VUS.
And to give you a sense of just how huge this problem is, look at this number, 4,771. That's the estimated number of newborns in the U.S. that would get flagged every single year for just one disease, Pompe disease, if we only use genomic screening. The vast majority are because of these VUSs, leaving thousands of families in this awful state of anxiety.
Okay, so you might be thinking, well, why not just ignore these uncertain variants then? Just focus on the ones we know are bad. The problem is if we do that, if we only report the confirmed bad typos, we risk missing kids who actually have the disease. As this quote points out, ignoring them could mean way more false negatives, which means telling a family their child is perfectly fine when they're not.
But here's the cool part. This chart, it shows us a way out. Researchers figured out that for Pompe disease, just by studying and clarifying what the 10 most common of these VUSs actually do, we could slash the number of flag cases from over 4,700 all the way down to around 1,500. It proves that with targeted research, we can make this data so much more manageable.
So how do we actually solve this whole VUS mess?
Well, it turns out the smartest people in the room are realizing it's not about choosing one method over the other, but about intelligently combining them. One really elegant solution is this two-step process. First, use the powerful genomic sequencing, like a huge, wide net, to catch anything that looks even a little bit suspicious. Then, for any baby that gets flagged, you go back to that very same dried blood spot and run the classic biochemical test. Right? The blueprint might have a typo, but is the factory actually producing a faulty product? That test gives you the answer.
Then there's another model, which is being pioneered in places like Italy's Apulia region. Here, they run both tests in parallel, right from the start. They're checking the factory's output and the blueprints at the exact same time. By putting both sets of data together from day one, they're hoping to get the most accurate, complete picture of a baby's health immediately.
And look, this isn't just some idea being kicked around in a lab. This is happening now. Major pilot programs are already running across the world, trying to figure out the best way to roll out this genomic revolution safely and effectively for everyone.
I mean, just look at what's already going on. You've got massive studies in New York City, in the UK, across Europe, in China, all sequencing the genomes of hundreds of thousands of newborns. These projects are the ones on the front lines, tackling the immense technical, ethical, and logistical challenges of turning this tech into a routine part of public health.
But, and this is where things get really serious, as we're pushing the boundaries of this incredible technology, we have to face a pretty tough reality. Even with the old screening methods, there's a huge global disparity. A baby born in Italy gets screened for over 50 conditions. A baby in parts of Africa or Southeast Europe, they might be screened for just a few, if any at all.
And that brings us to the most critical challenge of all. The fear, as this quote puts it, is that this powerful, expensive, new technology could make that gap even wider. We risk creating a world with a permanent genomic disparity, where the life-saving benefits of this revolution are a privilege reserved only for the wealthiest countries.
So at the end of the day, the ultimate question isn't just about which test is better. It's about access, it's about equity. As we continue to unlock the secrets of the human genome from a single drop of blood, the greatest challenge we face is going to be ensuring that this incredible power to save lives reaches every single newborn, no matter where on this planet they are born.